All right, good morning, everybody. Today I'm going to be competing in AtCoder Beginner Contest 174, ABC 174. Let's just make sure. Yeah, OBS looks good. I'll be competing live during the contest. The goal is to solve set, and hopefully we can do that, but we'll see. At the end of the contest, I'll explain my solution ideas for all the problems that I know how to solve. So if you're interested in solution ideas, you can skip to the end. I'll leave timestamps for all of those in the description. So anyway, contest started. Let's start reading the problems. Problem A, you want to turn on the air conditioner if and only if the temperature in the room is 30 degrees Celsius or above. Sounds pretty basic. Let's do it. Oh, this is some old contest. I'll figure that out later. Well, I guess while we're waiting for Eclipse to load, let's just read maybe the second problem as well. We have endpoints in the 2D plane. The coordinates of the ith point are x, y. Among them, we are looking for the point such that the distance from the origin is at most d. How many points are there? I see. Yeah, so we can do all comparisons in longs there to avoid using square roots. So that's probably a good idea. Guess let's read problem C as well, now that we've got A and B solved. Mine solved, at least. She loves multiples of 7 and multiples of k. What are the first occurrences of multiple of k in the sequence this thing? If it contains no multiples of k, print -1. Interesting. Interesting. That's not super obvious. Wait, what? What did they say? Or the first occurrences of multiple of k. The sequence. Do we print the index of it? Oh, I see. Yeah, okay. So I guess we can just solve this thing under mod. And it won't occur more than it won't take more than n turns to find. So that shouldn't be that big of an issue. All right, let's go solve A. So A, we wanted to check if the thing was 30 or more. So int n equals this out, n is greater than or equal to 30. Yes, no. Let's run samples. .5 is, the single test case. Good thing we ran samples. .5 is, what? 30? 25 is no. 30 is yes. Sounds good. There's problem A. Problem B now is count how many are this certain distance away. So, first we read in the number of points, then we read in the distance, now we can iterate through each point. if x times x plus y times y is greater than or equal to d, and C++. And then I think this is single test case as well. They want greater than or equal to d, right? Oh, at most d. Less than or equal to d then. And then I think we should be fine. Oh, we're not fine. Yeah, d times equals d. Okay, nice sample. Let's try this one as well since they're very generous. 7. Very good. 6. All right, I like it. Compile error. Yeah, that's a thing. We're gonna compile error for B as well then. So there's our new problem B. And then here's our new problem A. Okay, on to C. I think we can just count up to like 10 to the 7, and then if we don't find one, then quit. So let's try that. Target value equals this. Or I guess this is mod, right? Mod. Int val equals 7 under mod. Now, what if mod is 1? Yeah, so if if mod is less than 7, then sys out no, right? Or -1. All right, otherwise, we'll read in this value, which is the current value, yeah. And then, well, let's do this 10 to the 7 times. Start at 1. If val is equal to 0, then sys out I, and then break, or just return even. Otherwise sys out no, or -1, and then otherwise val equals val times 10 plus 7. Mod the mod. Looking good. I don't know that I have proof for that. But that's right, but wrong answer, huh? Wrong answer. Wrong answer means I must not be going high enough, right? 7 is the first thing. 77 is the second thing. What about like 10? Well, either I'm overflowing. Yeah, how is this wrong? Wrong answer? Can I see what this looks like? It's less than 7. Oh wait, that's not true. Yeah, this case is wrong. Because if it's 1, the answer should not be -1. Should be 1. Yeah, that's the problem. And everything else, it just takes order mod steps for us to hit a cycle for sure. Make sure to make this main so we don't compile error again. And I think we're fine. No, not even close. Did I even run samples? I didn't. Wait, did I even submit what I submit to? Rounds at 5 a.m. are a little early for me. Come on, where's give me my submissions. I submitted to problem A, that's the problem. Submit to problem C. This. All right, good. On to problem D, altar. Cool name. An altar enshrines end stones arranged in a row from left to right. The color of the ith stone from the left is CI, which is either red or white. You can choose 2 kinds of operations any number of times in any order. You can choose 2 stones, not necessarily adjacent, and swap them. Or you can choose 1 stone and change its color. According to a fortune teller, a white stone placed immediately to the left of a red stone will bring disaster. So you need a bunch of reds, then a bunch of whites. I don't think you ever need to swap them. Yeah, you never swap. You only change color. Yeah, okay. So this is easy, I think. So we can go from left to right and brute force where the split point is, because we want a bunch of reds, then a bunch of whites. We want reds, then whites. So here, what do we do? Well, how do we do this third one in 3? Maybe we do swap. No, we never swap. What am I talking about? Here's reds, then whites. So we turn the 2 whites to reds. How do we do this one? We want red, then white. This is a bit tricky. Okay, so we have white, red, white, white, red, white, red, red. Maybe my solution idea is wrong. Come on. So R white, red, red, white, white, red, white, red, red. And then we want a bunch of R's followed by a bunch of W's. So we need to delete what are the operations? Swap two things? Oh, choose any two and swap them. Got it, got it. Choose any two and swap them. So if we do that first, then we could do this next. Then we could do this next. No, we would do this one next. And we would have R, W, W, no. First, second, third, and fourth. W, 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 W. Interesting. How big is N? Pretty big. Well, this can't be that hard, right? Let's sanity check ourselves. What are the standings saying how hard this is? Yeah, okay, standings say this whole set's very easy, as it should be. It's an AtCoder beginner contest. Yeah, okay. So, so you do use swaps. Swaps are necessary, so my initial idea was wrong about those. Do you ever, well, I suppose, do you ever use deletes then? Yeah, why bother with deletes? They are equivalent in all cases, right? So we could either, if we have some white here, we might as well swap it with the last red. There's no reason to delete it. Yeah, okay, so deletes are unnecessary, so I was close. And then we can keep doing that, I think. Yeah. Yeah, that's fine. Okay. So let's do it. So first we're given an integer n, and then we're given all the colors. And n equals this. Int array colors equals this. So now char array rather, and now what do we want? Probably an int array of both, right? int array, well, array list, integer w's, and then r's. Capital W, right? Yeah. So it's capital W, then w's.add I, otherwise r's.add I. Okay. So now we want to remove w's from the beginning, r's from the end. For input string this, yeah, single test case. Index 2 out of bounds. W index is less than this. R index is greater than or equal to 0. Size -1, of course. Silly me. Yeah, I don't need to sort these because they come sorted. So this should be good. All right, problem E. Logs. We have n logs of length these things. We can cut these logs at most k times in total when a log of length L is cut at a point whose distance is whose distance from an end of the log is t, becomes 2 lengths of these things. Find the shortest possible length of the longest log after at most k cuts, and print it after rounding up to an integer. Yeah, so binary search the answer, and then iterate through each log. Then we're given k. Int array a equals fs.readArray n. Int ans equals, well, the min that the answer might be will be 1. The max will be 29 plus 100 maybe. So we just want to check if this is doable. So int mid equals min plus max over 2. If possible, the answer will be mid, a, and k is just k. So if it's possible to do this, then that means that our mid is, it can be smaller maybe, so max equals mid. Otherwise, if it's not possible, it's too small. So min equals mid plus 1. That looks good. Okay. So return k is greater than or equal to 0 for int I and a. K minus equals I or ants. Well, I plus 1 or plus ants minus 1 over ants. That is what we are looking for. That's how many cuts it takes to cut this thing down. We can use all integers here safely, I think. No. The answer 4 left with negative 8 is left with 0. Hold up. This might need to be the max of it and 0, right? We can make 3 cuts. So if I is less than or equal to the ants, then continue. Oh, this is how many pieces it'll be in, right? Yeah. So this minus 1, because we don't have to cut one of those pieces. Yeah, I see. Okay, that's fine then. Some number ends in 92. I buy it, and then we don't want this. Then this should be called main. All right, very good. On to the last task. Range set query. We have n colored balls arranged in a row from left to right. The color of the ith ball from the left is CI. You're given q queries. The ith query is as follows. How many different colors do the lth through rth from the left balls have? Interesting. Well, n root n is certainly possible, but also hopefully won't pass on this time limit. So we need something cooler. Yeah, that's a fun one. I like it. That's neat. That's neat. I like it. Good problem statement. How do we do that? We could do a persistent segment tree. Persistent segment trees would work. Feels like maybe overkill. I can certainly do it in a knower though. So if comes down to it, persistent segment trees work. We could answer the queries offline. Now we don't need persistence. Yeah. So if we answer the queries offline, we just need point update range sum, so we can choose a bit. Yeah, so you don't even need a segment tree even. So we answer the queries by left endpoint, and then we query how many numbers are less than or equal to some position. Yeah, all right. Cool, let's implement it. So I'm getting my binary index tree here, or Fenwick tree, if you prefer. We don't need get kth. We just need read. Yeah, I guess that should be fine, I think. So, oops, this is the wrong problem. So maybe there's just like the super wide variance in these contests, because this contest seems way easier than like the M solutions contest. Like the M solutions AtCoder contest seemed like it was very difficult compared to this. I don't know. Yeah, I think ABCs, just like despite being rated for the same range, are so much easier. But whatever. Query int x or int lr public query int l int r this dot l equals l, this dot r equals r, public int compare to query o, return integer dot compare l o dot l. Okay, single test case int n equals this thing, or nq equals this thing, for int q equals 0, q equals less than q equals plus. So I just wasted some time typing this because we don't actually need to sort them. This is going to be size n, int l equals this thing, r equals this thing, both one indexed. Query q equals new query from l to r. We need to store the answer here. Q queries at qq equals q, queries at l that add this thing. So now we have all of our queries sorted by left endpoint. We also need to read in this array. Are the colors of reasonable enough size? They're less than n, awesome. So int array last seen was new int array n plus 10 or something. Arrays dot fill last seen with n, and we also need a bit n plus 100. Just making my constants bigger and bigger. That's fine. So for int l equals n minus 1, L is greater than or equal to 0. This is the left endpoint of the query. So first we need to add it to the bit. So bit at last seen at A at L dot update, or bit dot update this thing by -1. Bit dot update this position L by +1. Bit dot update, nope, just last seen at A at L is equal to L. Okay, so now for query Q in queries at L. Yeah, so now q.ans equals bit.query or dot read q.write for query in queries. This out this dot ans. Okay. What else do we need to worry about? These are all null. Awesome. Two, three, one. Looks good enough. All right, so, oh, we might need print writer. I guess we'll see. We might TLE because we were greedy and submitted too fast. Yeah, darn. Print writer. How would it be? Print writer system.out. Print line, or I guess we don't need to print, just out.close. All right, this shouldn't be a problem because that's order n, right? Should be fine there. Very good. All right, so those are all of the problems. I don't know. I feel like it's pretty boring contest, to be honest. Not really a fan. But we're speed running until it's unrated for us, right? That's the goal, at least, the very least. And it's still rated for us. We're 177th, so it's possible that even still it will be rated for us, because 177th place on a contest that, I guess there are quite a few people. Yeah, I guess these people are all similar in rating to me. So maybe it's possible that we go up. But I really have no idea. 59 minutes left. So we'll talk about solutions. And then I think I'll just wait to upload this until the contest ends. That'll be the plan. So yeah, man, voice crack. That's what happens when you wake up at 4 a.m. Solution time. Problem A, air conditioner. So there's not really much to talk about here. You just print yes if x is greater than or equal to 30. Here's what that looks like. Well, let's change this to F so we don't have the warning. But yeah, you just check if x is greater than or equal to 30. If it is, you print yes, otherwise you print no. That's problem A. It's about as easy as it gets. Problem B, you might have issues with precision on it. So you want to make sure that, like, you want to check the magnitude of this vector basically. And you can do some like Pythagorean theorem stuff. So you want to check if this distance here is like greater than or equal to like 7 maybe. In order to do that, you want to check like this a squared and this is b squared. So you want to check the square root of a squared plus b squared and see if this is greater than or equal to, or I guess less than or equal to in the problem, less than or equal to c. Well, the square root introduces doubles, so you have to be careful. It's possible that with long doubles in C++ you'll be fine. In Java, I wouldn't trust it. And to fix that, what you can do is instead of square rooting this, you can square both sides, and now you want to compare a squared to b squared and c squared. That'll tell you which one's bigger. So you just do this for every point, and then if it's big enough, then you're good. Otherwise, you stop. Yeah, okay, so that's that. That's problem B. Let's talk about problem C now. Yeah, okay, so here's the thing here. If you have, like, yeah, okay, so you've got a bunch of different values, and basically, like, let's say this is 7, this is 77, this is 777, and it keeps going on in a circle. This kind of looks like a smiley face a little bit. Let's make it look less like a smiley face so I'm less distracted as I explain it. There we go, now it's a circle. Or a really, really big smiley face. Depends how you look at it. Like, this might be a huge, just very happy guy. Anyway, you have all of these positions, and you want to see when is one of these a multiple of k. Equivalently, that means when is one of these things modulo k equal to 0. So here's the important thing to notice whenever you want to go from one of these to the next. In order to do that, you multiply your value by 10, and then you add 7 to your value. So that's what we do every step between every adjacent pair of these. And eventually, if we keep doing that, there aren't that many values, that many different values, right? In fact, there are only k of them. We could be 0, 1, 2, 3, 4, 5, 6, 7, 8. But once we hit k, that's the same as being equal to 0. And k plus 1 is the same as being equal to 1. So we want to calculate the value of each of these numbers under mod. We can do that just by doing this times 10 plus 7, and then doing it mod k every step. And then we know if that cycles and hits a bunch of numbers but doesn't hit 0 ever, then we know that it'll never hit 0. Because once it hits back to this position, it'll keep going in the same cycle. And if that cycle doesn't include 0, it'll never include 0. We also know, since every node here has an out degree of 1, we know if it does include 0, it'll hit 0 in at most k steps. Yeah. So I guess maybe k minus 1, depends how you count. But that's the important part. So we can just simulate taking k steps. If we hit 0, or I just simulate like a bunch of steps, like 10 to the 7th steps. If you hit 0 in those steps, then you know the first time you'll hit 0 because you've simulated the first however many of them. If you don't hit 0, then that means you're in some cycle, and that cycle doesn't include 0. So even if you go forever, you'll never hit 0. So yeah, so the code for that, I guess, it's just like that. Here's the code for B. It's pretty simple, but the code for C is just take 10 to the 7th steps. If you see the answer, then print it. Otherwise, if you don't see the answer, just print -1. Okay, let's look at problem D. So here's the idea. What you want, basically what they say is you've got some string of red and white characters. Maybe it looks like this. And you want to like change this so that after some number of operations, you have a bunch of red followed by a bunch of white. Each operation you can do one of two things. You can either delete something or you can swap any two balls, not necessarily adjacent. So like this one and this one. Initially I thought they had to be adjacent, which is why I thought this swapping was never necessary. But it turns out that they don't have to be adjacent, in which case it's the opposite. The swapping is the only thing you do. The deleting is never necessary. So here's the reason for that. Let's say maybe we were considering deleting this ball right here. The only reason we would delete it is because there are a lot of white balls before it, and we don't want to have to like worry about, like we can't have a white ball before a red ball ever. So instead of deleting it, if we just take this and we swap it with the first white ball, that still fixes this ball here, and it also might fix some other red ball later. So we can use that exchange argument. Anytime we might want to delete some ball, the only reason we would want to delete it is because there are either red balls before it and there can't be, or there are white balls, or there are white balls before it and there can't be, or red balls after it and there can't be. And instead of deleting it, we could just replace it with one of those, like the farthest, most egregious other ball. And then later on, that might wind up being helpful for us. So we never need to use those deletions. Instead, we only need to use swaps. Since we're only using swaps, we can just do a greedy argument. That you always do the most extreme the other direction. You can do a similar exchange argument. I won't go through all the details, but it's like pretty much the same thing. And then the goal is just like simulate it, check how many swaps you would need to do. So in order to actually do that simulation, if you have all of the indices of all of the reds and all of the whites in sorted order, then you can just do a sweep. So you look at the first white ball and the last red ball, and then if you need to swap them, you do. But if the white ball comes after the red ball, then you are fine. Then you can just leave things how they are. You don't need to do any more swaps. So yeah, just get at the indices of all the reds, all the whites, and then swap them as long as you need to. And that's it. All right, problem E. So yeah, okay, so you've got a bunch of logs, and you want the longest possible log to be as short as possible. After that, you want to round it up to the next integer, and then you want to print how long it is after doing that. So you can actually do this all with integers, and then you just want to see, can everything be this length or shorter? And if the answer is no, then you would have like decimal amounts that would be trailing or whatever. And then you can handle those decimal amounts by just like you could put them all in one log if you wanted to, or you could put them in a bunch of logs and then round all of them up. So I just chose to, let's just make everything integer amount since we're rounding up anyway, and then we don't have to deal with doubles at all. Very good. So how do you actually do this? Well, we're going to binary search the answer, and once you know how long this log is going to be, so maybe this is like what it is initially, and then we say this is the maximum length of our answer. This is going to be some integer, because we said we're going to be working with the integers so far. So we can make a cut here, because we know we could keep all of this log, and that would be fine, but then we have to cut it eventually. And then we could cut here again, because we need to keep this much, and then we'd be fine, and then we'd cut here again. So it might seem like you want to cut the log evenly, but it doesn't actually matter, because if all we're doing is looking at the maximum value, then we basically just want to spend as few cuts as possible on this log in order to not have it become like illegal. So we can easily calculate how many steps this is going to be. If the log has like length L, and then this is like some length W maybe, then we just need L divided by W. We need this many logs, but we also need to take the ceiling of this because you might have this extra bit left over. So this is how many pieces it's going to be in. In order to make this many pieces, you need to make this many minus 1 cuts. So you need to make one fewer cut because you don't have to make a cut for this piece, right? You can assign each of these cuts to the piece that would be to their left, and then you have the one extra piece that you get for free. Similarly, if you have a log that's just one piece, then that costs 0 cuts. Yeah, so if we binary search the answer, then we just need to be able to check, is this answer possible? And we can check just by looking through each log, counting how many cuts it would take, and then that's our answer. Let's look at the code for that really quick. So here's just the binary search. We have the minimum possible answer and the maximum possible answer. We check if some answer is possible. To do that, we just look through all things in the array, and then check if the total number of things used is less than or equal to k. Very good. That is problem E, and then one more problem, problem F. I think this was like the only interesting problem of the set, maybe. I liked this problem. The rest of them I thought were a little bit boring, but that's fine. So, yeah, you've got a bunch of colored balls, and you want to see for each query how many different colors of balls are in some range, some continuous LR range. So in order to handle this, we can look at each query by its left endpoint. This is a pretty common trick, but it's really helpful. And let's consider some range here. Maybe this is our range. If we know we want to look at a query at this left endpoint, basically what we want to say is how many colors are in some range. I guess that's exactly what we want to say. That's the problem we're answering. But we can look at a simpler version of this problem, which is if we only, let's imagine we were ignoring this array for now. Now we want to say for each color, if you only look at the first element of that color that comes after this, the question is how many of those first elements come before this right endpoint? So that's the problem we're trying to answer. How many of the first elements after this come before this right endpoint? Now, if we have a set, if we know what all of those first elements are, then really we just want a range sum of how many things are in these values. We can do that with a Fenwick tree. We can also do it with a segment tree, or you can use, if you actually have a set, like a multi-set, you could use the policy-based data structures. Then you don't have to write anything yourself. Java doesn't have that, unfortunately, so we write our own Fenwick trees. But yeah, that's the goal. So if we want to actually answer the query, once we have this stored, we just do a range sum of these values, and then we can see, all right, whatever that is, that's the total number of different first color values there are, which is the same as the number of different colors in this range. Then, the only other part of the question is how do we update this left endpoint? So if we wanted to update the left endpoint going right, that would be possible, I guess, with some pre-computation. But for me, I thought it was easier to update this left pointer going to the left. So when I do that, I keep everything that's to the right of me. So I keep all of the elements to the right. But then for the things to the left, all of these things that come before me, they stay outside of the range. But now we've just added this extra element. So when this happens, we might need to delete some previous element. And I keep a lookup table of when was the last time that I saw each element. So what is like the current index of each color in the array? So if this was the last color 2, then I remove one of this index from the list of first indices, right? So maybe like this is color 2, this is color 4, this is also color 4, this is color 3. So then in my table, I'll have like one table here, which is like the last time I saw each color. So 0 we haven't seen, 1 we haven't seen, 2 we saw at index 2 we saw at index 4, 3 we saw at index 5, 4 we last saw at index 3. And then we'll also have this thing, which is like number, or like I guess this is like things less than or equal to. Well, I guess this is just like a frequency array of this array right here. So here we have 0, 1, 2, 3, 4, 5, and 6. We've got 1, 4, 1, 5, and 1, 3. So really, this is a binary index tree, not an array, but it's easier for me to draw it as an array and think of range queries on it. So that's what this is doing. Okay, so when we want to include this 2 here, what we do is, let's say this number, instead of being like, well, if it's like a new number, let's say it's like a 0. Well, let's say it's an old number. Let's say it's a 2. I think that makes it easier to demonstrate. So what we need to do is remove this 2 from the frequency array, and then we want to replace it with this. So I look up in this last seen array, I look up the last time I've seen position 2, and that was at index 4. Which means this index 4 here, I need to erase and make this a 0 in my frequency array. Then I need to make the last time I saw 2 be position 2, which is right here, because that's the last time I've seen it. And then finally, I need to update position 2 in my frequency array, so I make this a 1 here. All right, now when I want to answer a query, I just want to see, so now I've stored all of the things, I've stored, let me clean this up a bit, and then I can show you what this frequency array is storing. Storing this position here, because this is the next 2, this position here, which is the next 4, and this position here, which is the next 3. So that's why these all have 1s in them. So if I want to answer some query, for instance, how many colors are in this range, then I can do a range sum on all of these values, and there are 2 values that have 1 bits, or that have like 1s, right? So the sum will be 2, and that'll give me the answer that I'm looking for. So yeah, that's the idea. The actual code for it is pretty simple. Here's, or it's problem F, right? Yeah, so here's the last seen array. I have all of my queries. I put them in different buckets for each left endpoint. And then after having them in different buckets, I do exactly the 3 operations that I said earlier. Yeah, my query is just like this, and then here's my bit code. I'll scroll through it, and you can pause it if you'd like in order to see that. I'm pretty sure they're also open submissions, so you can just see the code that I submitted as well. All right, so that is AtCoder Beginner Contest 174. Yeah, I enjoyed problem F. I thought the problems were a little bit easy. It's kind of more of a speed run than a programming contest, in my opinion. But I hope you enjoyed. I hope you maybe learned some things from problem F, if that was new to you. And I also hope that I make it to being unrated, but we'll see for these contests. I might keep doing them just because they're a little fun, but that's the goal, obviously, right? Get to, I guess it's not even Div 1, right? There's even a higher ranking than this. Get to the point where only AtCoder regular contests and AtCoder grand contests are rated for me. That's the goal. Eventually, the long-term goal for AtCoder, at least, is get to the point where only AtCoder grand contests are rated. But I think that'll be quite a while. So we'll see if this is enough. I'm not going to wait 40 minutes until we actually know. But yeah, we'll see. That's all. If you have any questions, feel free to I'll post a link to this video in the Codeforces blog post. Usually there's like a Codeforces announcement for these ABCs. So I'll post a link to the video there. You can comment if you have any questions, and then I'll try and get back to you on those. The comments of YouTube videos don't work super well for asking questions, so maybe put it back in the Code Forces blog post. But yeah, thanks for watching. That's all from me. Have a great day, and hope you enjoyed. Goodbye.